joke that was, I don't know if you remember, if you ever saw this movie, you don't remember because before you were born, I think. This movie called Real Genius, and students are, it's kind of take off and count back, and the students, are at the beginning of the class, the lecture hall is just completely full, everyone's there. And then, over time, people are kind of not going to class, instead there's a little tape recorder on their desk. This is there. And, recording the lecture, and, over time, more and more people have gone there, more and more tape recorders. And then it's all tape recorders, and then the professor is just talking to the tape recorders. And then at the very last scene, the professor is a tape recorder talking to the tape recorder. So,
it's a valid term.
yeah. When he was anyway, welcome to all right, so let's get started. We will have one more problem set. That problem set will be an extra credit assignment. Okay? As I mentioned, the material that we're talking about right now will not be on the exam. But it's very important nonetheless. So I have to go back to DC this weekend. I'll be on Monday and Tuesday. So we won't have lecture on Tuesday. So your choice. What would you prefer? Do you want to do lecture Wednesday morning or Wednesday late afternoon? Morning. I'm for that. All right. So we'll in room 190. I'll double check. From what time did we say? 9:30 to 10:45 a.m. Okay. All right. Very good. That'll be an important lecture. So we're going to do Fermi's Golden Rule next week. So that's important to be there for that. All right. So let's see. Where were we? Oh yeah, we were here. So when we were talking about spin magnetic resonance, we looked at this paradigm where we had a strong magnetic field along some direction called the z-axis, and there's a weak magnetic field that oscillated in the transverse plane, and if we had it rotating, it had this form. And we saw explicitly here the terms that went like e to the minus I omega t in interaction Hamiltonian were associated with flipping the spin from spin down to spin up. Right? So that was what we might call absorption. And then there were terms that took you from that went like e to the plus I omega t, and they lowered the spin. They were what you might call emission terms. Of course, as we discussed, really in this description, it's all just unitary evolution according to the time-dependent Schrödinger equation. Things evolve continuously in time and intermediately are in a superposition state. In fact, we just oscillate back. In this picture, there's nothing irreversible happening. Okay. When we had the magnetic field oscillating linearly along some axis like the x-axis, then we saw this kind of time dependence in our interaction Hamiltonian, where there were terms that looked just like this. Those were the co-rotating terms. And then there was a counter-rotating term. And these are terms that correspond to resonant coupling, because when we went into the rotating frame, that canceled this time dependence. And then we got a strong accumulation. We had resonance. Whereas these terms oscillated so quickly, I claim they don't contribute strongly to the dynamics. And in fact, the farther away from resonance we are, the less important, the closer to resonance we are, the less important these terms are. So,
when we wrote this down, we had sigma plus, sigma minus, and then the next two terms had e to the 2i omega t. But it looks like you factored something off, but it's not on the outside.
This is in the lab frame. So when we go to the, so you're absolutely right. When we go to the rotating frame, what happened is this goes like e to the minus, e to the plus I omega t, cancel that. So that's exactly right.
Okay.
Yeah, no, that's good clarification. Thank you. So you should really think about the rotating wave approximation as a combination of perturbation theory, as to say that we're looking at the Rabi frequency being small compared to the resonance frequency. That's to say the interaction strength is weak compared to the bare energy string. That's one part of the rotating wave. And the other is that we're very close to resonance. Then the counter-rotating terms are negligible, okay, if we're close to resonance. That's the rotating wave approximation. All right. Here's another NA. All right, so the next thing we discussed last lecture was how any resonance between two quantum states is isomorphic to the problem of spin to magnetic resonance, mathematically described by the same mathematics. Anyway. And so in particular, if we look, for example, at shining a laser beam, which has is monochromatic, has a single frequency in it, tuned it close to the energy difference between two energy levels of an atom, or a molecule, or a solid material. And it's really, if it's just described by those two energy levels, then, and those are connected by, say, whatever, it's an allowed transition. In this case, we're considering it to be an electric dipole transition, but it could also be an electric quadrupole transition if we wanted to. Then we can restrict the dynamics of the system to just those two levels, because those are the ones that are resonantly coupled. The others are just negligible because they're so far off resonance. Okay? And when restricted to that subspace, the atom Hamiltonian has this very simple form. It's just the two energy levels, etc. Right? And if we then make this mapping, we call this a pseudo-spin. We say this is a two-dimensional Hilbert space. It's as if this were to spin up and spin down of a spin 1/2 particle. And then we can write the operators that are restricted to this two-dimensional subspace in terms of Howland matrices. Okay? They have nothing to do with the state of the electron. They're just a mathematics that describe this operator when restricted to that space. Okay? And the interaction Hamiltonian couples these two levels. If this is, let's say, an electric dipole allowed transition. And it has only off-diagonal matrix elements. And those off-diagonal matrix elements depend on the coupling trains that I've taken to be real, in this case, that matrix element. And this thing that flips round to up, and thing that's excited to, down to up and up to down, or vice versa, is the Pauli sigma x operator, right? And so we see exactly this kind of picture that we had here. And you'll notice, again, we would, under the assumption, as we are for the two-level approximation, that we're close to resonance, we would make the rotating wave approximation, right? and just keep the term that goes like e to the minus I omega t with the thing that's associated with absorption. And the part that goes like e to the plus I omega t, like the thing that determines emission. That is the rotating wave approximation. All right? Okay, so with that, we turned our attention to looking at the more general formalism now for time-dependent perturbation theory. Okay, so our setting is we have some system like an atom or a molecule or a piece of solid-state material, and we are going to drive it with some external fields. Okay, and those external fields are going to perturb the system. Well, they will shift the levels. There will be AC energy level shifts. But most importantly, typically, we're interested in how the system evolves dynamically in time due to the fact that the system is no longer in the eigenstate of the Hamiltonian. Okay? So it might start in the ground state, and then we shine on this microwave or whatever on it, and something happens. All right? So what we're really interested in here is solving the time-dependent Schrödinger equation. So to do so, what we did is a lot of rigmarole here, where we said to solve this efficiently, it's convenient to take the part of the dynamics that is, in some sense, trivial, that we know because we've solved for the energy levels of the bare system, and take that out of our description of how the state evolves and shove that into the evolution of the operators. Okay? So the operators evolve according to H0 in this case. And then the state evolves according to the interaction. Okay? The interaction in the interaction picture. So let's say that. Okay? So this is our time-dependent Schrödinger equation in the interaction picture. And the solution to that is just given by some unitary time evolution operator, where that time evolution operator is the unitary operator generated by the interaction Hamiltonian. Okay? So this is an expression for how this is the infinitesimal translation in time is that Hamiltonian, in this case, in the interaction picture. And we wrote down a formal solution to that as a power series solution, which is known as the Dyson series. And it's our starting point now of time-dependent perturbation theory, because we see that this is a power series in different numbers of powers of the interaction Hamiltonian. All right? Now, just, there's many ways we can write this solution. This is the Dyson series solution. In the special case, let's look at the case, suppose, let's just, before I do that, let's just look at these terms more carefully. So let's look at the second order term. Okay. What are we doing here? We're integrating this over 2 times, right? So if I think about the integration area here, there's t prime and there's t double prime. We're integrating over 2 variables, integrating over that plane, right? And this is the line t prime or t double prime equals t prime, right? So I'm integrating this as t prime goes from 0 to t, And then for every value of t prime, I only integrate up to t double prime, right? So this is the integration I'm doing. Right? That's the integral. Now, there is I can write this, there's another integral I could do. So if I look at the integral of, let's say I look at the integral over the whole region. So this is dt prime, and this is dt double prime. So that's the integral over the whole square there, right? Which is, of course, just the square of one of these guys. This is the same thing twice. Just give it a different dummy variable. So this is equal to the integral over the two triangles. I have the one that we just wrote down. Plus, I can integrate here. This goes from 0 to t, and t double prime goes from whatever value of t double prime is up to t. So this is t double prime, and then t prime goes up to t double prime here at h t prime h and t double prime. So I just broke up the integration region over the square into the integration over two triangles. Now note, I didn't commute these, because I can't necessarily do that. If I can commute, okay, this is actually a wrong statement, because they don't commute. This is true, right? The integral over the two regions breaks up into the integral over the two triangles. But I can't necessarily switch the order of the two Hamiltonians. Okay? If they commute, so if the interaction Hamiltonian commutes with itself at different times, then this thing is equal to the integral 0 to t double prime h int t double prime times the integral up to t double prime dt prime h int t prime, right? So if that were true, then I could write it in this order. And in that case, then this equals this. It doesn't matter what the dumb variable is. So when the Hamiltonian commutes with itself at different times, then it doesn't matter what order I do it in. I can integrate over this triangle or that triangle. In which case, the integral over this piece over here, which is equal to a half the integral, so over the whole square, up to t dt prime h int t prime squared. So that's if the Hamiltonian commutes with itself at different times. And the same thing would be true for all of these guys. Of course, there are 3 factorial different permutations of the order in which I can write these things. So this integral, if they commute with itself at different times, would be 1 over 3 factorial times the integral cubed, etc. So the end result of this is the following. If the Hamiltonian commutes with itself at any 2 different times, T1 and T2, for all T1 and T2, then the interaction evolution would be the following. The sum over n, 1 over n factorial, minus I over h bar to the power n, integral 0 to t dt prime, the interaction Hamiltonian, in the interaction picture to the power n. Okay, that's only true if this is true. Yeah.
Isn't this an exponent?
It is, exactly. So this is equal to the exponential of this. Okay. So when this is true, we can just write the Hamiltonian, the time evolution operator is just the exponential of the integral. Okay. For example, suppose my interaction Hamiltonian was the following. I have some mu b magnetic field along the x direction that varies in amplitude sigma x. Does that commute with itself at different times? Yeah, because it's just some amplitude times sigma x, right? So the reason when we had this where this went like cosine omega t sigma x and sine omega t sigma y, that wouldn't commute with itself at different times because the Pauli matrices associated with different directions in space don't commute with each other, right? And we couldn't do this. But when it does, we have this kind of expression. Okay. Now we can write the Dyson series as one often does, and this is particularly important in quantum field theory, in terms of a formal expression known as the time ordering operation. So the time ordering operation is the following. It says if I take the time ordering operation on 2 operators, some operator A at time t1 and some operator B at time t2, that this, by definition, is equal to the product of these operators if t1 is less than t2, and it's equal to this if T2 is less than T1. So it just says put the operators in this order depending on the order of time. And I'm going to leave it to you show, fairly easy, it's a little bit tedious, but you can go through it yourself, to show the following is true. That generally, I can write my interaction evolution in the following way. So you will often see the solution to the time-evolution operator written as what's called the time-ordered exponential. This is the general solution. You will often see it written this way. So each one of the terms, if I come back to the Dyson series over here, what I would have is I wouldn't have, all of these integrals would go up to the same final value. They all integral from 0 to t. But then I would have the time-ordered product here. Similar here, I'd have the time-ordered product of these three things. It's a useful way of dealing with it as in terms of writing finding diagrams, frankly. In other words, we sometimes just write this down just as a shorthand to say we have to be careful when this doesn't commute with itself at different times. Yeah,
Just to clarify, this is in the interaction picture, right?
This is all in the interaction picture. Yeah, I'm being so tired of writing all my declarations.
Yeah, I just
but
wanted
you're
to make
right.
sure.
We have to. It's important, and we're going to. It's absolutely true. Yeah. Thanks for. Yeah. Indeed. All right. Now, I just want to connect this to one other way you will see this described. For example, if you look in Cohen-Tanucci's text on this subject, it's what's sometimes known as elementary theory. You know, this is Dyson series and interaction picture seems somewhat complex and overly so. Why do we do all this stuff? Here's a little bit of intuition why this might seem a reasonable thing to do. Let's look at the relationship between the state in the interaction picture and the state in the Schrodinger picture. So let's recall. So what we did is we took the state in the interaction picture. We obtained by getting rid of the free evolutions, the trivial evolution from H0 out of the Schrodinger picture. That's how we defined it. Okay. So let's say that so let U sub n be eigenstates of H0. So we can always use this as a basis. They have eigenvalues. That's to say, these guys are eigenstates with eigenvalues of E0. These UNs form a basis. Okay? So I can write, say, the Schrodinger picture evolution as some superposition. These are the Schrodinger picture hold on a second, I need to check something in my notes. Right, so these are Schrodinger picture coefficients, right? So I just expand this in the basis, where C sub n, this evolves according to the total Hamiltonian. That's the total Hamiltonian, that's a Schrodinger picture. All right? Now, what is the state in the interaction picture? So according to this, I apply this to this thing. And what is that? This is e to the plus I h0 t over h bar, right? This evolves simply with that phase factor, right? So this is then equal to e to the plus I en 0 t over h bar un. Now, this I can expand in terms of, there's some other set of coefficients that I'll call the interaction. So there's some, in the interaction picture, I can expand this in basis with its own set of coefficients. Okay. And so what I see here is that if I relate this as that in the interaction picture, the expansion coefficients are related to the expansion coefficients in the interaction picture with this fixed trivial phase. So putting that all back together, I get the following. In the Schrodinger picture, now, when you see this in a textbook, often these little labels won't be put there. You'll just say, I'm going to make an ansatz. I'm going to say, let me just say that the state at time t is some expansion of coefficients e to the minus I Pn0 t over h bar Cn. That's how you'll often see this written. So this is saying the following thing. If I make this ansatz, what we are saying about the state is, if there was no interaction, then we would just have some initial expansion in the eigenstates of h0, and then each one would evolve by this trivial factor. Now I turn on the interaction, and I say the effect of the interaction is just some slow modulation of the Baire frequencies. And then I just have to solve for these guys, having taken out of the time dependence the trivial time dependence that I know is there from the free evolution. And then I just solve for the remaining time dependence. So I've kind of factored out the time dependence I would have had if I just had a 0. Formally, what we're doing is this. We're looking at the expansion coefficients in the interaction picture. Okay? So if you go and you look in your textbooks and you see what is the connection, that's what it is. Okay, so with all of this said, now we want to actually use this formalism to calculate something. All right? So what we're interested in is we're going to calculate the probability to transition from some initial eigenstate of H0, call that I, to some final eigenstate of H0. F. Okay. So these are two eigenstates, U sub I and U sub F. They're the eigenstates, they're like the energy levels of the atom. And we want to know what's the probability. So at time t equals 0, the state of the system in any picture, say the interaction picture, is I. And I want to know what is the probability that I'll find it in F. So I go from I to F. How would I calculate that at time t? Let's say capital T.
Apply it squared.
Apply what?
Apply the raw onto our evolution.
That's right. So we want to know the probability that I'm in F. So the state here is, this is the state T in the interaction picture squared. That's the probability I'm in state F. But what is this? Well, that's the time evolution operator applied to that. So what I want is the matrix element. That's my transition probability. This is at time capital T. So this is the probability that at time t, I find the system in that eigenstate of. Now we can look at that based on the Dyson's series expansion of U, right? So this, plugging in the Dyson series expansion, I'm going to have, this is going to be equal to the sum over n, sum C n Fi T squared, where C Fi n is equal to the nth order power of that. So that's the transition probability amplitude. To order n in the Hamiltonian. So, what is the 0th order transition amplitude? If we look at that, that's equal to that, right? Which is 0. right? Unless it's the same state. What's the first order one? So we have minus I over h bar, the integral 0 to t prime, capital T, less u, the matrix element of the interaction Hamiltonian in the interaction picture, less u dt prime. That's my transition amplitude to first order. And to second order, integral 0 to t dt prime, integral 0 to t prime, t double prime, or I could put it in the time ordered exponential, but I'm not gonna. Etc. So what I have here is transition amplitudes to different orders in the interaction. And perturbation theory says as long as this is a small perturbation, the smallest non-vanishing term dominates. Yeah.
I'm sorry, you did that really fast and I didn't quite follow it. So here the sum that you're looking at is not the same sum as over there,
No,
right? It's
no.
it's a sum over the perturbation.
It's that power series.
Okay.
So this is the zeroth order, 1, 2. Or I can look at it this way. It's this end,
Okay.
right?
Sure. So then, I guess you did in the.
Forget about that. This was, we could write this, I'm not using this at the moment.
Okay.
I could do it this way, but that's not what I'm doing. Okay, I want this, I was just showing you this here to show how when you read this in some textbook, what the heck does this have to do with the Dyson series? But I'm not using this at the moment. I'm just saying I'm using this. Okay?
Oh, okay. I'm sorry.
Yeah, I'm sorry if I made that logical leap. It's the same thing. I guarantee you can go through it and do it the same way, but we're using here the Dyson series. Okay, so perturbation theory tells us that we can calculate the transition probability in different orders of the interaction strength, assuming that this is a convergent power series, as long as these terms are small compared and goes down. And that we'll have to come back to that in the same way that we talked about time-independent perturbation. Remember, we had some problems when we had energy denominators, all that stuff. Come back to that. Okay. So, but under the assumption that this converges, that this is small compared to that, then we can look at the lowest non-vanishing term. Okay? So let's look first at first order time-dependent perturbation. So we just have to calculate that integral of that matrix element. So my transition amplitude to first order is equal to minus I over h bar, the integral from 0 to t, dt prime. And then I'm going to plug in there. So I have the matrix element of H in the interaction picture. And now I'm going to explicitly, and that's why it was really important to keep track of that. That interaction Hamiltonian in an interaction picture involves this free evolution. So this is in the Schrödinger picture.
And those are T primes?
They're T primes, yes, indeed. Thank you for that. Okay, now, these are eigenstates of H0, right? So they evolve with the trivial phase, e to the minus I energy, right? So this is equal to e to the minus I e sub I over h bar t prime, right? And this is e to the plus I e final. I'm going to drop the zero, that stupid zero there. Those are, I will be clear, the energies that we're talking about are the energies of H0. Okay. So, with that, I can write this as minus I over h bar, the integral from 0 to t, dt prime, e to the plus I omega fi t times the matrix element of the interaction Hamiltonian in the Schrödinger picture, where omega fi is the Bohr energy associated, or the Bohr frequency associated with that energy difference. T prime. Okay. Doesn't really matter. It's a dummy variable. You can call it anything I like at this point. All right. So, what do you think about that? Well, this kind of looks like a Fourier transform, right? Fourier transform is the integral of some function of time respect to that. If I'll just call this thing h f I t prime, just make that matrix. Okay. So it looks like the Fourier transform of that, but it's not quite. Because the Fourier transform goes from minus infinity to plus infinity, right? However, it is the Fourier transform of the following. If I write this in the following way, I can integrate this from minus infinity to infinity. And now I'm just going to get rid of the primes because there's just a dummy variable. A windowing function where e to the I omega fit, where this theta function is 1 if t is between 0 and capital T and 0 elsewhere. Okay, so this is just a function that just cuts off everything that's not inside the window of time between 0 and capital T and is 1 there, okay? So, now I ask you, because you are all masters of the Fourier transform, what is the Fourier transform of a product of two functions? The convolution of the Fourier transforms of the two functions, right? So this is equal to minus I over h bar. The convolution of the Fourier transform of the windowing function evaluated at that frequency with the Fourier transform of this function. This is my symbol for the convolution. So, the convolution of the two functions. So recall, the convolution of two functions is given by the integral where I shift one function relative to the other, integrated over all, or equivalently. Either way. Okay. So, we got to find that. Firstly, so let's look now at a specific case. Let's consider the case where our perturbation is some oscillating field that oscillates monochromatically at some driving field of the perturbation. For example, our problem of a laser with some electric field that's oscillating at some definite frequency. All right? Just gonna get rid of this because better to use the front board. So, consider harmonic driving. At frequency omega drive. Okay. So, my interaction Hamiltonian is going to oscillate at that frequency. It's a Hermitian Hamiltonian. And I can always thus write it as a part that goes like e to the minus I omega t and a part that goes like e to the plus I omega t. Any function that oscillates with some frequency can always be written that way. So this has a term which is typically called the positive frequency component. That's not a dagger, that's a positive. As a function of time. Oh no, there's no time dependence here. Is that? And the Hermitian conjugate is the negative frequency component. Okay, so this is known as the positive frequency component. And the negative frequency component. It must be the case that H minus is the Hermitian conjugate of H plus. So if it oscillates that frequency, it will be of that form. All right. So what is the Fourier transform then of that? We have to get a different symbol when you get this, excuse me. So I take the matrix element of this, I take the matrix element of that, and now I Fourier transform it. Indeed. It's the sum of two delta functions, right? So the Fourier transform of this is a delta function centered at that frequency. And the Fourier transform of this is centered at minus omega c. So this is going to be equal to h plus fi times 2 pi times a delta function centered there, plus h minus fi, a delta function centered at minus square root of pi, where we define our Fourier transform.
Is that like an omega fi?
Yes, this is, so evaluated omega fi, then that's what that is. I mean, this is a function of its argument. Okay. So, just sketching that, of course, it's a trivial thing. As a function of its argument, there is a spike here at the drive frequency and at the minus of the drive frequency. This is the Fourier transform. That's my picture of the delta function. All right? Yes, sir.
When you say negative frequency component, what do you mean?
I mean exactly this, that its spectrum lies at minus omega. So that's, I mean, when we have a real function, its Fourier transform will always have frequency components in the positive frequency range and in the negative frequency range. They have to come in pairs in order so that when you add them together, it's depending on whether it, either pure imaginary, pure real, depending on odd or even functions.
So this isn't like on negative frequency at least?
No, it is not. It's about the Fourier components. So this has Fourier components at positive frequencies. Now you say, but this got even more than sine omega t. Why is it positive? That's just because of the way we define it. All right. So that's this. So then we have to take this and convolve it with that, right? And get the transition amplitude. Okay? So what is the Fourier transform of a window function? It's not a door. Anybody know?
It's a sine.
Something like that.
It's a sine or a cosine.
Not quite. It's a sinc function. It's a sine x over x function. Yes, exactly. There are windows are mnemonic, I remember that. So let me explain. The Fourier transform of the window function is that. Okay? And that is an integral, since this is only zero, I mean it's only non-zero between those, and it's the integral from 0 to t, right? This then is equal to e to the I omega t minus 1 divided by I omega. So, what I'm going to do, because I'm a tricky one, is I'm going to factor out an e to the I omega t over 2, and that's e to the I omega t over 2 minus e to the minus I omega t over 2 divided by I omega. Right? And then, because I'm even trickier, I'll put a t over 2 here, and put a 2 here, and a t there. Okay? So that's sine, so that is equal to e to the I omega t over 2t times the sine of omega t over 2 divided by omega t over 2. Which is sometimes called the sinc. So sinc of x is sine x over x. So what does that function look like? Do you remember? It's something like that, yeah. So firstly, what is sinc at 0? It's 1, right? Because good old the hospitals rule. So the sinc is 1 at 0, and then when it's equal to pi, it's 0. So it kind of looks like, then it has this 1 over x envelope. So it looks like that, right? Let's wait for it's 2 pi. We'll wait that max. All right, so you may remember that this is the diffraction pattern of a single slit. That's because the diffraction pattern is the Fourier transform of the shape of the slit. So if you just have this is the window, and we pass through that, what you see is that, okay? Now, what is the convolution of this function with this? Isn't this fun? Knowing your Fourier, this is something that is unfortunate. Undergraduate physics education does not emphasize enough Fourier analysis. It is so important. So we need more practice with it. Well, let me ask you, let's just do another little aside over here, in this little corner of the board. Suppose I look at the convolution of some function of t with a delta function centered at t0. Okay? This is going to be equal to the integral dt prime f at t prime convolved with, or t minus t prime convolved with this, which is f at t minus t0. So when you convolve a function with a delta function, it just centers that function there. Okay? So I'll just draw it here now. So now this is what I have, and let us assume here that the time, the width of my function here, when I look at it over here, this function has a width in omega that's like 2 pi over t. Right? From what we just said, because this width was on the order of 2 pi, pi or something like that. So let's take the time that I calculate this probability transition to be sufficiently long compared to the period of oscillation of the drive. Because if it's not long compared to the period of oscillation of the drive, I don't see the fact that it's monochromatic at all. I need to have many oscillations before it in any way looks pseudo-monochromatic. So I'm going to take this to be big compared to the period of oscillation of the drive. Okay? Which means that the width of this function omega is narrow compared to omega b. So my function will look like that. And this is not so narrow, but this will be the same. So that's what this looks like, where this width over here is on the order of 1 over t. So, what we see, so let's write it out. there they are. Thank you. Thank you, sir. All right. Where are we? Oh, no. Right. Okay, so my transition probability to go from the initial state to the final state at some time capital T will be equal to the following thing when I plug all of that in. 4 times all right, let me explain. So what have I done? So, when we come back over here, when we did this convolution, these are going to be things that look like the sinc function centered at, say, omega d, right? And this, if I write this as a function of omega fi, is omega fi. Okay? So that's, and so then I square this function to get the probability. I assumed that the cross terms were negligible because I assumed that the tails of this are so small that I could just square this and the product between them is 0, and that is based on this assumption. Okay. So that's what I have. That's what these two terms are. Now let's examine them a little bit more carefully. And I rewrote in this case, I got rid of my h bars by absorbing them. This was omega fi times h bar. There was one for h bar squared that came from the thing, so I absorbed that h bar squared into here. And similarly over here. So let's notice this term is going to have big amplitude when this is close to 0, right? And you can see that here. The sinc function is biggest when omega fi, so this is biggest when omega fi is equal, right? Which is to say that the final energy is equal to the initial energy plus h bar omega drive. Okay. This thing is biggest where omega fi is equal to minus omega d, which is equivalent to saying that initial energy is equal to the final energy minus.
Aren't those two statements the same?
No, it's the other way around. The final energy is the initial energy, right? Because this minus that. Yeah. So, what we see is this term dominates when you have absorption. You go from a state with a lower energy and you increase by 1 photon of quantum of energy associated with the drive frequency. This term, the term that went like e to the minus I omega t, e to the plus I omega t, the negative frequency, is related to emission. Where whatever my initial state, I go to a state with a lower energy, taking away 1 quantum of energy, H1. Okay. So, what we have in perturbation theory is exactly what we saw before. The terms that went like e to the minus I omega t are associated with absorption. The terms that go e to the plus I omega t are associated with emission. Of course, this is in the near resonance approximation, which is equivalent to the rotary wave approximation. Now, if we go back over here, what we note, of course, is that the amplitude and then the square of this, the probability for us to make this transition is not exactly 0 once we fall off resonance. There's a kind of width to this. In this case, the width is due solely to the time over which I observe it, or as you say, I interact with it and try to measure it, right? So there's a kind of what we call time energy uncertainty principle here. It's not quite the same kind of uncertainty that we studied in the context, of position momentum, because there's no operator that represents time. So it's not about not moving. This is really just Fourier duality, right? I mean, a function which is longer in time, the window is longer in time, in frequency it's narrower and narrower. So there is this, but if I want to, and you're seeing this in your homework, if you want to measure a frequency that's related to an energy difference between two systems, and you want to do that precisely, so you don't want any uncertainty in your measurement, the longer you measure it, the better you can know the frequency, right? Because what you're really doing is looking at oscillations, and you want to see whether two oscillations get out of phase or not. They're very close to one another. You can't tell that until you go many, many oscillations, and eventually you'll see that phase building up.
Is that like the Shannon-Nyquist statement, like is that related to that at all? Or how often?
Yeah, that's a little bit of a different deal. That's to do with finite sampling. Okay, that's not what this is really about. This is just saying if I want to, there's something that has a natural resonance frequency, and I want to measure what that frequency is. I drive it with something else that is its own oscillator. I want to see whether those two oscillators are in phase or not. I can measure that more and more precisely the longer I go. Okay, so in the problem for homework, what we have is two oscillators. One is the spin or the atom has a natural resonance. The other is the microwave cavity. You're trying to see when the microwave cavity is on resonance with the spin. And you do that to see whether it gets to the excited state or not. That's the transition amplitude we're measuring. Okay? And the longer you measure it, the better this is. The better you can, more precise you can make that measurement. Now, I just want to conclude with one further statement. Notice in this problem we have, as we did in time-independent perturbation theory, these energy denominators, right? The energy denominators that we had in time-independent are like this, but now
because we have this extra part that's coming from really the photon, if you like. So it's the energy of, the degeneracy of initial plus photon is final. What happens if I'm right on resonance? Well, I mean, this doesn't break down, right? It doesn't go to infinity because this goes to 0 too. But it's not necessarily going to be a perturbation. I mean, the perturbation, assume that this was small, right? Now, when this ratio is not small, this isn't necessarily perturbation. We have to be very careful about that. So right on resonance, say for absorption, this thing goes like, you know, the matrix element. Oh, this is backwards. Sorry. That's correct. And then this thing goes like, well, if I put back in the t over 2 squared and the t over 2 squared, right? Then this becomes the sink, and that becomes then t squared.
So, aren't the H's Hermitian?
They are.
And the order not matter?
Well, no, these are not Hermitian. H is Hermitian, but the plus and minus is not Hermitian. So the dagger of this is equal to that. So it doesn't matter. Yep, but good point. All right, so just to conclude, what we see here is that if I'm right on resonance, then that's what this probability is. It grows quadratically. And only for short times is this a perturbation. For long times, this sure ain't going to be a perturbation, right? This, of course, is just if you remember, we had Rabi oscillations, the probability to go from ground to excited state. We have this kind of sign. We're just looking at the quadratic part of the Rabi oscillation. Just like we did in time-independent non-degeneracy period, when we have a resonance, which is equivalent to a kind of degeneracy, we really have to then just say, fine, we'll just look within the subspace of a degenerate system, which in this case is the two systems connected by the laser, say. And just solve there and forget about it. And then we know the solution. It's Rabi oscillations. Okay? Perturbation theory breaks down. Unless it doesn't, and we'll do that. All right. Hang in there. There's final stuff to